Good afternoon, everyone. Thanks, Mr. Chairman. Ladies and gentlemen, it's my pleasure to be here presenting our research about FRP shear friction reinforcement for concrete joints. I'd like to acknowledge my co-authors, Dr. Faouzi Ghrib, my colleague at the University of Windsor, who's here on the hall, and our two graduate students, Mr. Alkatan and Mr. Alruwaili. And I am Ragaby, an assistant professor at University of Wisconsin in Platteville. I know it was a long day. I will try to make it as light as possible. The typical content will go through a little bit of introduction, some literature review, the motivation and the design of the experimental program, test results, and our final conclusions. Accelerated bridge construction, it's a very famous approach for bridge construction, and the most adopted system is the girder slab type. We have pre-cast, pre-stressed girders, and most of the time cast in place concrete slab. To get the best out of the system, we need the girder to be composite with the deck slab, and we need to ensure the compatibility and the composite action, which require ensuring the full transfer of the longitudinal shear between the deck and the slab. And this is currently obtained by providing a lot of shear or friction shear reinforcement or horizontal shear reinforcement, which is made out of steel bars. The bridge deck slab, as a typical case in North America, is subjected to one of the harshest environmental conditions worldwide: freeze-thaw cycles, extreme cold temperature, de-icing salt. The bridge deck, as a typical case, needs to be demolished from time to time and totally recast again. And as that connection for the shear friction is part of the slab as well, it is subjected to severe corrosion as well. The practice used to be by using epoxy-coated reinforcement, which unfortunately had proven over the time to fail mitigate this problem. And this is what was found after several years and extraction of epoxy-coated reinforcement. It's already damaged because this is just a coating. Any crack of this coating is peeling. The bar itself is exposed. And that's why Ministry of Transportation of Ontario in Canada, as well as many DOTs in the States, started banning the use of epoxy-coated reinforcement. The possible solution here is extending the application of the very well-established FRPs nowadays to replace or to work as shear friction reinforcement and to get use of the favorable non-corrodable nature of FRPs. As we know, the FRPs are totally different than steel. We have to establish and study their performance in that situation. So the main objective is to study what would be the effectiveness of using glass fiber reinforcement as shear friction reinforcement in concrete connections, investigate their behavior and what is the influence of different parameters such as the type of reinforcement, the geometry of reinforcement, the reinforcement ratio, and hopefully trying to understand the behavior and develop some design guidelines. Shear friction and shear friction theory. This theory has been established since early 1960, and in its simplest format, the hypothesis is that we have a concrete joint, two concrete that are cast at different times. Under flexural stresses, we need to transfer the compression force in the slab with the web itself for the full composite action. The assumption that we have a rough surface between both of them. Any tendency for slippage between these two surfaces is due to the roughness, is trying to push the two pieces apart. And here is the role of the reinforcement. The reinforcement there, or the shear friction reinforcement, will provide a clamping action to tie these two parts together, and this clamping action will boost the shear force and enhance how much shear that interface can carry, as you can see with these schematic diagrams. In the first early version of the shear friction theory, all the attention, all the credit for the shear strength of this interface was just given to the reinforcement itself. The shear strength of the interface is just the coefficient of friction with the ratio of the reinforcement times F yield. No consideration had been given at all to the friction carried by the concrete itself or by the cohesion of the concrete. After several iterations, the research has been carried since 60s until recently to apply several development and several improvements for the shear friction theory. In its most recent current format, the shear strength is attributed to the cohesion of the concrete, then the coefficient of friction multiplied by the clamping stresses, and this clamping stresses is the amount of the reinforcement times the yield strength of the steel, plus credit for any extra external clamping stresses due to any other sources. This contribution of the concrete here arises from two sources. A cohesion, which is, if we assume, if we imagine this is a close-up for the rough surface of the concrete, the local roughness here, this is the main source of the cohesion of the concrete, and the general roughness where the reinforcement will activate and ensure that there is no big gap so that these two surfaces are still interact together. This will contribute collectively for the shear strength of that face or that interface. The most famous way used to develop the theories over the years are by simply carrying the test over a very simple but yet famous push-off specimen, which was adopted in our approach. As per the current literature about the general behavior of shear friction reinforcement out of steel bars, the full load slip behavior or stress slip behavior can be categorized in multiple linear stages. The first stiff behavior, when is attributed mainly to the concrete and only up to the cohesion of concrete. Once the stress developed increase further, the cohesion will be destroyed, then the friction of the concrete itself will start to take the credit for resisting the load. Once a shear crack developed at the interface between the two parts, and if enough reinforcement, enough shear friction reinforcement was provided, the interface will start or will continue carrying more load, but at a much less post-cracking stiffness, until the point where the steel reinforcement totally yielded. Sudden drop pressure failure will take place at the interface. That is the general behavior as indicated in all the previous studies, and some minimum recommendation had been provided for how much is the minimum steel reinforcement to ensure that you will have some post-cracking strength from the specimen or from the connection itself. As a summary of the finding of the literature, the main parameters that affecting the shear transfer across concrete to concrete joint can be classified as what is the total clamping stresses coming from the reinforcement or any external sources, how much is the roughness modulus of the interface, and in some time the quality and the strength of the concrete itself can control or can contribute to this stresses. And this drives us to try to investigate the effect of these parameters once we use a GFRP as a shear reinforcement at that interface. We design our experimental program to carry tests on the simple and efficient push-off specimen consisted of two halves, two L-shaped specimen. They are cast at different time. For example, you start by casting the first half where the shear reinforcement is oriented there. After curing, you can cast the second half. We adopted different values for the cross of the contact area of the concrete to generate more reinforcement ratio, as we'll see shortly in the test parameters itself. The specimen, each side was heavily reinforced to eliminate any shear or any flexure cracks in the specimen itself due to the loading and a very stiff steel plate. The cross section of each L shape was 250 by 250 in dimension, and the contact surface, we vary the contact surface between 300 millimeter to 500 millimeter in length. The testing parameter, we tested the reinforcement stiffness, and this parameter actually contains two values here. What is the Young modulus of the J4B reinforcement that is used, and how much is the reinforcement ratio, as the reinforcement as the ratio between the cross-section area of the J4B over the contact area of the concrete. We investigated two concrete strengths, 50 MPa and 30 MPa, as well as different shapes of J4B bars in forms of stirrups, in forms of headed bars. Also, we tested some angle shape, 90-degree angle of J4B bar, but this is not part of the presentation today. The stiffness matrix consisted of 3 series of specimens for a total of more than 30 test specimens. In series A, this is where the contact surface was 250 by 300 by 500 millimeter long, and the concrete strength was 30 MPa. We tested a plain unreinforced specimen, a reference specimen reinforced with 2 steel stirrups, then some specimen reinforced with J4B stirrups, so F referred to FRP, S referred to stirrup. We used 2 and 3 and 4 J4B stirrups. Then F refers to headed bar, H refers to headed bars. We tested another specimen with the same interface of 30 megapascal with 3, 4, and 5, and 6, and 8 J4B headed bars. Series A2, this is where we eliminate or reduce the length of the interface. Instead of 250 by 500 here, we went to 250 by 300 just to generate more reinforcement ratio. And again, we have a plain unreinforced specimen, steel specimen with 2 stirrups, J4B stirrups, 2 stirrups and 4 stirrups, headed bars 4 and 5 and 8 headed bars. Series 3, A3 here refers to high strength concrete, and we allow me to use the term high strength for just 50 MPa, but to differentiate between series 1 and 2 as 30 MPa and series 3 was 50 MPa, and also we repeated several specimens. Out of this test matrix, we try to generate a test specimen reinforced with J4B stirrups, a test specimen reinforced with headed bars, which yielded the same rho V times the Young modulus for comparison of the effect of the shape of the J4B reinforcement itself. Also, we have with 2 interface area, 250 by 500 or 250 by 300, we have also 2 specimens with the same stiffness modulus or stiffness factor as we call it. Another time, we, in some cases like here, specimen with 2 J4B stirrups, we repeated it 3 times for the repeatability and more confident in the test result, as well as we repeat also 2 of the 3 headed bars reinforced specimens. Material properties for the J4B bars, it was a V-rod, J4B stirrups, and the Young modulus from type 1 with Young modulus of 50 gigapascal. The headed bars had a Young modulus of 60 gigapascal, and that's why, due to the difference in the Young modulus, we decided to evaluate the value of rho times E, rho times the Young modulus to have as a reference. The steel stirrups, the details of the steel stirrups as per their typical yielding properties. Fabrication of test specimens, we build a formwork. We cast the first bottom L shape, longitudinal and L shape, where the reinforcements are in position. Then this is the shape after casting. And all the time, we didn't pay any special attention to the preparation of the contact surface. We kept the contact surface, which is the top surface of the bottom specimen, or the bottom surface of the top specimen. We kept it as cast. We don't prepare any special roughness, any special preparation. We kept it for all the specimen the same. Then the cage of the top specimen has been arranged, casting the top part and curing the full test specimen with reference cylinders for test. For testing the specimen, we adopted, beginning in phase number 1, we adopted test in a vertical direction, resting on a very stiff steel piece, resting on the strong floor, and pushed against the hydraulic jack. This system gives us the ability to apply up to 600 kilonewton, and all of a sudden some specimen exceed that capacity, and we have to shift to test the specimen in a horizontal direction against a strong wall and a stiff frame. And to make sure that we don't have any constraint from the floor, we put the specimen on rollers on slender steel tubes, make sure that everything is very smooth, there is no extra constraint. The main instrumentation was just 2 strain gauges just at the middle of the bar, exactly at the level of the interface between the 2 specimens, as the critical point for stresses and strains as indicated by previous studies in steel reinforcement, as well as each specimen is provided by 2 long LVTs on each side to measure the relative slip between specimens. In terms of test result, this diagram represents the behavior of unreinforced plain concrete specimen out of 50 megapascal. And as you can see, it can be categorized as 2 bilinear stages. The first stage when only have a cohesion. After the cohesion is destroyed between the concrete, then the friction takes place up to a certain limit. No reinforcement after the limit of the friction. The specimen failed suddenly without showing significant resistance. Adding 1 FRP stirrup, 2 FRP stirrups, 3 FRP stirrups, as you can see, the behavior keep improving in terms of how much is the ultimate loaded carry, in terms of how much is the post-peak performance. For 1 FRP stirrup, yes, it enhances the pre-cracking stiffness a lot, enhances the ultimate load a little bit, but after a physical crack has been developed at the interface, 1 FRP stirrup was not enough to resist that amount of shear, and the specimen failed suddenly. Having 2 stirrups, the post-peak behavior have some more deformable behavior. As not only more deformable behavior, you can see how much load it sustained. More than 90% of the original load that sustained it after the physical crack took place, and even after this crack keep growing more and more. FS3 with 3 FRP stirrups, this is when we were testing it vertically. We hit the maximum capacity we can obtain, around 620. We couldn't initiate a failure for this specimen. Comparing the behavior with a steel reinforced one, we can see specimen SS1 reinforced with just 1 steel stirrup, specimen FS2 reinforced with 2 FRP stirrups. And we can recognize still the ratio between the young models or rho times E is still significant. Steel here is still more than twice rho times E, more than specimen reinforced with 2 FRP stirrups. Still, it show 2 FRP stirrups gives, or we're able to give a comparable ultimate strength and comparable stiffness to the single reinforced steel specimen with just one steel stirrup, and both of them, after the initiation of the crack, they're weak. The reinforcement content was not enough to carry the load, and they failed suddenly. The specimen reinforced with 2 steel stirrups, of course, showed a higher load, but when we compare it with specimen reinforced with 3 FRP stirrups, still the ratio between the stiffness of the reinforcement here is maybe 3-4 times for the steel one higher than the FRP, but on the other side, the FRP one is still carrying or show much higher capacity, and this can be attributed mainly to the perfect linear behavior. Once the steel specimen hits the yielding strength of the steel, no source for that clamping stress, we have already developed a lot of lateral strain and lateral separation dilation of the specimen. It failed suddenly, which was not the case with the FRP stirrups. The same can be also derived from specimen reinforced with headed bars. The plain unreinforced specimen, 2 headed bars, 3 headed bars, and 5 headed bars. 2 and 3 headed bars were considered inadequate reinforced specimen. That's why they didn't show significant increase in the strength after the crack initiated, while 5 headed bars show significant increase. If we'd like to look at the overall behavior of load slip behavior for the FRP reinforced interface, it's very, very comparable to the steel one, but they have more significant or most advantage here, which they are able to sustain much higher level of load after the initiation of the crack due to the linear behavior of the J4B or FRBs in general. This slide here gives just an idea about the nature of the failure. This is a failure mode of unreinforced specimen. This is the failure mode of steel specimen reinforced with 2 steel stirrups. All of a sudden, once there is yield, no remaining or no residual strength, while the one reinforced with 2 J4B stirrups, the specimen is still able to carry much load and sustain that load for a long time after failure, on the expense, of course, of more strain and more dilation in the specimen itself. I have to quickly here. What we notice also in the behavior, this is what we verify as a cutoff limit for the adequacy of reinforcement. If any specimen was reinforced with a reinforcement parameter less than 253 MPa, it doesn't have enough reinforcement to carry the stresses after failure. While when the reinforcement content was more than 253, after the cracking here, you can see the specimen is still able to either sometime gaining more load, maybe due to the dowel action, or at least sustaining the load for a long time. And the peak load in most cases took place around 500 microstrain measured in the GFRB reinforcement. In terms of difference between shape, effective shape, these 2 specimens with the stirrup and with the headed bar, both of them has the same stiffness parameter, and they show almost a typical indication. So it's not the shape, it is the reinforcement content or the stiffness of the provided reinforcement. All these specimens, you can tell, with stiffness inadequate reinforcement, after cracking, it failed suddenly later on. In terms of the concrete strength, for low concrete strength, increasing the reinforcement ratio doesn't have a significant effect because the concrete is weak. It cannot match the strength provided by the J4B itself. While in case of higher strength concrete, this is 3 J4B stirrups, this is 50 J4B stirrups. We have more stiffness from the J4B and we have more strength from the concrete as a parameter or as an effect of its friction capacity. You can expect up to 61% increase in the stiffness. The same for the headed bars. Headed bars, 3 for 30 megapascal, 3 for 50 megapascal. There is no big change comparing the effect for low strength concrete, but for high strength concrete, significant increase with the increase on the content of the JFRB itself. In general, if we look at the final summary of most of the test specimens, increasing the axial stiffness or the stiffness parameter E times rho V, increasing it for the J4B bars, the maximum capacity transferred over the cross section increased significantly as well. We tried to derive an equation to predict the shear capacity of J4B reinforced interface, and we tried to have the equation in the same, following the same format of the current steel one. And these are the result of all the test specimen divided by the concrete strength versus the ultimate stress as a dimensionless factor. We found that the cohesion of the concrete, which should be the resistance at 0 content of reinforcement, equal 0.04 times F prime C. The coefficient of friction based on the slope of the line here combined with the recommended level for stress in the J4B for the design as the stress at 5,000 microstrain or 0.5% of the ultimate strain times the Young modulus multiplied by the reinforcement ratio, and this gives, we can say, a closer to lower bound for the strength of that interface. And this is the proposed equation for designing any concrete interface with J4B reinforcement. In a nutshell, we can draw few conclusions. That test results showed that J4B reinforced interfaces as shear friction showed a comparable effectiveness compared to the steel reinforced ones. The reinforcement stiffness was found to be the dominant factor. It's mainly due to the perfect linear characteristic of J4Bs, despite or against the yielding of steel reinforcement. And the minimum recommended reinforcement content to ensure that we still have some strength and sustain the load after the failure should not be less than 253 megapascal. And higher complete strength would result in a higher shear transfer capacity and stiffer peak load response. And the slab of the shape of the reinforcement itself was not found to have a great effect compared to the stiffness parameter itself. The slab at all the adequately reinforced specimens, the slope between the two interfaces doesn't exceed 1 millimeter, which meet most of the specification in most standard. Before I conclude, I would like to acknowledge the contribution of Fultrar by providing the VROD. I'd like once again to thank my co-author. Thank you so much for being here. It will be my pleasure to be able to answer any questions you might have.